Hi, welcome to a podcast on percent composition, empirical formulas, and molecular formulas. Today we're going to learn how these tie into moles. If you need help with moles, you can go back to the Mole Problems podcast. And if you've seen this picture, this couple is moving some boxes. They're mailing them some things to their relatives. And let's say in the boxes on one of the side, they have one computer and 2 mittens. So there's 3 total items. Now, how would they, if they went to the post office, how would they be charged? They wouldn't be charged by 1, 2, 3 different items. In other words, this mitten right here is not 1/3 of the whole shipping fee by mass. There's 1 out of 3 items. 1 is a mitten and 3 total items. 1 is a mitten and there's 3 total items. And 1 is a computer and there's 3 total items. But that's not how the post office charges you. Goodness no. They charge you by how much it weighs. So that's exactly how percent composition is tallied up. You figure out what the part is over the whole by mass times 100. If you just did this part over the whole, you'd have a ratio. To actually find percentage, you need to do part by mass over the whole thing by mass over 100. And I already know that out of this box, if they were milling a computer and 2 mittens, that the computer would definitely have more mass. It would take the largest percentage of it. So let's look at this. Okay, so a percent composition, again, is a mathematical method that's used to determine the percent of each element by mass, just like going to the post office in a compound. And so if you look, this is part over the whole times 100 equals percent composition. So let's do this for a formula. You know this formula is sodium chloride. So I know sodium's mass, and let me actually use a different color so you can keep track of it a little better. Okay, let's use blue. Sodium's mass on the periodic table is 22.99 grams. And chlorine's mass is 35.45 grams. And if you add these two together, my total mass of my whole compound is 58.44 grams. Now, how would I figure out the percent composition of sodium and the percent composition of chlorine? And you would be right by saying there's 1 sodium and 1 chlorine, but sodium, just like the computer and the mittens, is not an equal partner or equal mass to chlorine. So the way you do this is you take the part that's sodium, 22.99 grams. That's how much sodium weighs in this compound. And you take getting ahead of myself. Sorry, I got distracted. So you take 58.44 grams, that's the whole thing, and then you multiply that by 100. And when you do your math, which I'll do in a minute, that is the percent of sodium in this total compound. Now if you look, in chlorine, what do I have? Chlorine's heavier, isn't it? So it's going to take up more percentage-wise of my part over my whole. So this is how many grams of chlorine I have. This is how many grams of sodium chloride. This is how many grams of sodium. This is how many grams of sodium chloride. Part over the whole times 100. Again, if I just left the fraction, I would have a ratio. So when I do my math, I'm going to end up with 39.34% sodium. And when I do my math, I'm going to end up with 60.66 grams of chlorine. And if you notice, these two numbers add up to equal 100%. Let's try a harder one. So here I have aluminum hydroxide. Again, we're doing percent composition. The problem would say something like, find the percent aluminum in aluminum hydroxide, or the percent oxygen. So aluminum is Al. It's a positive 3 charge. And my polyatomic ion's hydroxide. It's a -1 charge. They're not going to play ball equally, are they? So throwing 3, catching 1, I'm going to have to write a 3 down here because I need 3 of these to play ball with 1 aluminum. All right, now how do I find out my percent composition by mass of each of these? Well, a little different. I have 3 different elements. I have aluminum, I have oxygen, and I have hydrogen. Now, I need to figure out how much aluminum I have. I have 1 aluminum, don't I? 1 here. And I have 1 here, but I have 3 oxygens. And I have 1 here, but I have 3 hydrogens. So 3 times hydrogen's mass, 3 times aluminum's mass, and, by oxygen's mass, and 1 times aluminum's mass. So in the periodic table, under aluminum's mass, it's 26.98 grams. Under oxygen, I have 16, and that's going to be a total of 48 grams for oxygen, because 3 times 16 is 48. And 3 times 1.01 grams in the periodic table is 3.03 grams for hydrogen. So now, before I go any further, I need to add all these up to get my total, which is your gram formula mass, isn't it? 78.01 grams is the whole thing. That's the whole compound. So how do I do my math now? I do my math by saying 26, let's close this, there you go, 0.98 grams of aluminum over 78.01 grams total equals, times 100, equals 34.59%. That's aluminum. For oxygen, I'm going to take 48 grams of oxygen over 78.01 grams. That's the mass of the total compound, times 100, and that's going to give me 61.53%, and that's oxygen. Okay? And how do I do my last part? Well, it takes 3.03 grams of hydrogen over 78.01 grams for my total, times 100, and that's going to give me a percentage of 3.88%. And that actually makes sense, doesn't it? Because if you look, my total mass is 78.01, and my hydrogen is only 3.03%. That's a tiny percent. That's why it matches up with that 3.88. Okay? What's my heaviest? My heaviest element total is oxygen at 48 grams out of 78, and that's why my percentage of oxygen is the most, 61.53%. So that's how you do percent composition. It's pretty straightforward. Part over the whole times 100. So now let's move to empirical formula. An empirical formula is the simplest whole number ratio. So, if I told you that I had a compound like this, C6H12O6, glucose, is that the simplest whole number ratio, the empirical formula? In other words, can you simplify that? If you look, I can take a 6 out and make that CH2O, or one of these for every 2 of these and 1 of those. Doesn't that match up to equal this compound? Now, this right here is called the empirical formula for glucose. It tells me the simplest formula, the simplest ratio, but it doesn't tell me exactly if this is all I know. In other words, I can't tell you what compound I have. Could my compound, if my empirical formula is CH2O, could it be glucose? Sure it could. Why? Because if you multiply this by 6, you get C6H12O6. What would happen if I multiply it by 4? Couldn't I also have C4H8O4? So, these are possible formulas, possible molecular formulas, but we're looking at an empirical formula, the simplest whole number ratio. And that empirical formula is the same for both of these. Now, let me ask you a question. Is this true? If this is my empirical formula, is this a possible compound that could fit? C5H14O2. Well, let's look and see. If that's true, then I'd be multiplying my carbon by 5, which would make this CH2O H2O. We'll make this 1 times 5, so that works. So it works for carbon. What's 2 times 5? It's 10. There's not a 10 here, is there? That's a 14. So this empirical formula cannot match up with this compound. It can only match up with these two, because there's a multiplier that you can multiply this CH2O by to get the new compound, the actual compound. So again, simplest whole number ratio is a simple formula for a compound. Now question, if I have water, H2O, that is what water is, isn't it? That's the molecule of water. But guess what? It's also the empirical formula. Same thing for carbon dioxide. That's the molecule. It's also the empirical formula. It's a simplest whole number ratio. You can't go any smaller. Well, what about for glucose? C6H12O6. Can you simplify that down? Yes, you can. To CH2O. This is not what it really is, but it's the simplest whole number ratio. So, now I'm going to give you a poem. You need to write this down, and I got this from the Journal of ChemEd many years ago. I kind of modified it a little bit. And this is the directions. It tells us to do percent to grams, grams to moles, divide by small, then round to a whole. So let's use this poem to help us out. And the reason, by the way, why I can do this percent to grams part is if I have a sample of a compound, I could have a tiny spoonful, I could have 100 grams full, or I could have a huge swimming pool full. And in each case, if I have a total, I have 100% if I have everything in the spoon. I have 100% if I have everything in the cup filled up, right, everything in the spoon. And I have 100% if I have this whole pool filled up. But how convenient if I have 100 grams and I have 100%. If I have all of my 100 grams, and that means that 100 grams equaling 100%, that means 1 gram equals 1%. That's why this step works. If you understand that right now, that's good. If you don't, then don't worry about it for right now, and we'll just move on and use this poem to help us solve problems, and we'll come back to that later. So, what do I need? Percent to grams. That means I'm physically going to take this word